Okay, so it would be a valid question to ask, why do we need exponents? I mean, what's really the purpose of an exponent? An exponent is the little number at the top of another number or a variable. We call it the power. Exponents, they allow us to represent really large numbers in a really small space. So if you can even imagine back in the time before there was any way to record anything other than writing it down, and you had really, really large numbers that you had to write over and over and over again, or use them in calculations, it would take up a lot of paper, or a lot of animal skins, or a lot of stones, just to do what you needed to do. No wonder some people would just give up. But with the invention of exponents, it made it possible to write really, really big numbers in a very small space. For example, the number 1 million. Now, if you had to write that over and over again, it would get pretty tiresome after a while. It would take up a lot of space on your paper. But it can be rewritten as 10 to the 6th power, taking up a whole lot less space, taking a whole lot less time to write it. And it actually becomes easier to use in calculations. 5 million then, or 5 with 6 zeros, can be rewritten as 5 times 10 to the 6th power. Again, making it easier to write, record, and also to calculate with. Also, the rules of exponents allow us to use these large numbers in calculations without a great amount of difficulty. If you had to sit down and multiply 3,500,000 times 7 million, I have no doubt that it would take you a few minutes to do, but you could do it and generally get the correct answer. But imagine if you had to do that over and over again with numbers such as these. The rules of exponents allow us to rewrite something like this as 35 times 10 to the 5th times 7 times 10 to the 6th, which still, it's kind of an involved multiplication problem, but still not so insurmountable, not taking up as much space as the former. This can also be rewritten as 35 times 7, and then 10 to the 5th times 10 to the 6th, and then the 2 multiplied together. This, by the way, would be the answer. Or, if you choose to write it out in longhand. Now, I've been at this math game for a while, and my salary still hasn't reached this point. In fact, if you go to right here, put a 1 right here, all these zeros behind it, you would never ever have to see Mr. Mackey again. That's not going to happen, right? Okay. So some things that we need to know. What does the exponent really mean? What's going on here when you put a 2 above a number or above a variable? Well, take for example, 8 to the 2nd power. The 8 is called the base. The 2 is called the power or the exponent. So in our discussion, when we talk about the base, we're talking about this number or this letter right here, and the power or the exponent will be the number at the top, the postscript. This is read as 8 squared or 8 to the 2nd power. And what it means is that the exponent tells us how many of the base numbers are going to be multiplied to each other. So if it's 8 to the 2nd power, that means take 2 8s and multiply them to each other. So 8 squared, or 8 to the 2nd power, means 8 times 8 which also means 64. 8 times 8 is 64. 5 to the third power means take 3 5s and multiply them together. So 5 to the third equals 5 times 5 times 5. 5 times 5 is 25, times 5 more, 125. 5 to the third power is 125. A to the fourth, whatever number A represents, it means take it and multiply it together 4 times. A times A times A times A. X to the second power means X times X. And by the way, these A's here and these X's, when there is no power written above them, the power is 1. They each have a power of 1. It's like coefficients. If a coefficient is 1, we don't write it because it would be redundant. This would mean 1 a to the fourth power. If we don't write the 1, we can still read this. There's 1a here, and it's raised to the fourth power. There is 1 x to the second power. We don't need to put the 1 in front of the x. And the same is true for anything having an exponent of 1. If the exponent is 1, we just don't write it. Now, one of the important things, there are many, but one of the important things to remember with exponents is when adding or subtracting terms, the bases must be the same and the exponents must be the same. For example, in this addition problem, we have x to the second power, x to the second power. Both bases are the same, both exponents are the same, so we can go ahead and put them together, and that equals 2x squared. To wrap your head around what's going on here, think of these as objects. You have one of these objects here, x squared, and you're adding it to one more of the same object. 1 plus 1 is 2. And here's the object. We have 2 of these objects now. The bases, the exponents must be the same to add or subtract. 5 of these objects plus 2 more of those objects. Bases are the same. Exponents are the same. 5 plus 2 is 7. We have 7 of those objects. Exponents do not change when adding or subtracting. We started out with x to the second power. We ended up with x to the second power. The power did not change. The number of objects we had with that power is what changed. Oftentimes, we will be working in simplifying polynomials, and we will have variables or numbers that have exponents. We just put them together with what they are like with. For example, 5x squared minus 2x squared, we can go ahead and combine those because they are like terms. They both have x to the second power. 5, take away 2 is 3. We end up with 3x squared. So we look for like bases and like exponents. So here we go. Here's an expression. 3x squared plus 2x minus x squared plus 6x plus 5. Now you may be shaking your head. Your head may be swirling on the inside. It's okay. Take a deep breath. Here's what I like to do. Start at the very front. I've got an x, and it has a power of 2. So I'll go through the entire rest of the expression looking for x's to the power of 2. And here's another one. So it's 3. Take away this 1, x squared. 3x squared minus x squared. Now I've identified all the x squares. Now I go to the next type of term. Here's an x to the power of 1. There are 2 of them, 2x. I go through and I look for more terms that have x to the first power. And here we go. Here's 6 more. So it's 2 plus 6. That's how many x's to the first power I have. So altogether, I've combined these two, and that just leaves the 5. The 5 has no variable with it. There is nothing that I can put the 5 with to increase or decrease it. I'm going to regroup my like terms, get them together. It'll make it a little bit easier to do the operations. So what we pulled out of here is 3x squares, and we're going to subtract 1x squared, 2 x's, and we're going to add 6 more x's, and then the plus 5 at the end, and it has nothing to combine with. So doing those basic operations, 3 take away 1 is 2, have 2x squares. Positive 2 plus 6 more, plus 8x. The plus 5 has nothing to combine with, so it just comes down into the answer. So to simplify this expression, here you go. 2x squared plus 8x plus 5. Can go no further in simplifying. Without something like this. I've got these groupings here. It's 7t to the 4th plus 5ab. And from that we want to subtract 6s plus 3t to the 4th minus 2ab. So we already know about this. This minus sign on the outside of the parentheses you can think of as multiplying by -1. And we also call that distributing that negative sign through the parentheses. It basically changes the sign of everything on the inside of the parentheses. So this becomes 7t to the 4th plus 5ab minus 6s minus 3t to the 4th plus 2ab. Now we can start here at the beginning and try to match things up. I have a t to the 4th power here, and I have more here. When I rewrite this in just a minute, it's going to be 7t to the 4th minus 3t to the 4th, and they're going to be together. I have 5ab, and then way down here I have 2 more ab. Those two also will get put together next to each other in the next step. And then finally I have this minus 6s. And there are no more terms with s. So it is not going to be combined with anything to change its form. Now we regroup. We get all the t's to the 4ths together, the ab's together, and the s down there at the end. Lonely, lonely 6s. Now we do the simple calculations. 7 minus 3 gives us 4t to the 4th. 5 plus 2 gives us 7 ab's. And then the minus 6s combines with nothing, so it just gets brought down here. And actually, this should be written in order of exponent and then alphabetically. But this will suffice for now.